Hi class, it's Jamie Batts, your instructor for Bio 221. This is going to be chapter 27, and we're going to go over part 1, the first couple parts of the chapter. The chapter starts with a description of body fluids and solute concentrations within the body fluids, and it differs between men and women. But overall, just like with everything, men have a little bit more of everything and women have a little bit less. It just has to do with our general body makeup, and that's on average. The charts that are on page 989 that cover the actual blood volume compartments and concentrations of solutes, you don't need to know those specifically. You should be familiar with like the major ions and minor ions and kind of where they are in the body, but you don't have to know the actual numbered concentration. So in other words, if I said something like the major cation that's extracellular, you should know that that's sodium. If I said the major cation that's intracellular, you should know that's potassium. So, you know, just kind of have roundabout numbers as a whole on your head, in your head. You don't have to know actual number values and concentrations for things on that chart. Moving into the chapter, it then goes into how your body regulates body fluid, and it does that by urination, right? Your kidneys are the way that your body gets rid of extra fluid, which is what we just talked about in chapter 26. So a lot of this stuff is fresh in your knowledge bank, and we're going to build on it a little bit. And that little graphic on page 991, it's the effect of blood osmolality and blood pressure on thirst. That is a very good image to kind of understand and know. So I'm not going to go through it for you. You can see the steps 1, 2, 3, 4, and it even paraphrases what those steps are in that little graphic there. You may want to look at that, see if you can summarize it, or put each of those steps on an individual note card and then see if you can get the steps in order so that you know what causes what, kind of that whole physiological process. It's very important to understand how thirst is regulated. The next little section is on, well, I guess the next page shows the cause and effect, kind of the homeostatic balance physiological process that takes place for the regulation of blood osmolality, and that's on page 993. So what you have, and you can work this kind of up or down, right? If you have a blood osmolality increasing, then you see how it's taking you through all of the steps. What's going to happen? Your hypothalamus is going to detect that increase, and it's going to signal the secretion of ADH. Well, then what does ADH do? Then you get into the reactions. ADH is going to decrease water absorption and all the stuff that's happening in the collecting duct. That's going to increase, basically water consumption increases. You want to build your blood volume, increase the water content in your blood, and then your blood osmolality decreases and homeostasis is restored, right? And then that process can happen in the opposite way. Just like with the other diagram, I suggest taking this diagram that's on 993, diagramming it out, and flowcharting it into individual steps so that you understand both sides of the homeostasis loop, so to speak, there. Then the next page is blood volume. So blood volume and blood osmolality are very linked, right? Osmolality is just dealing with the concentration of solutes in the blood, and blood volume is dealing with the actual amount. And blood volume, of course, is related to blood pressure. So it's the way, one of the major ways your body regulates blood pressure is by regulating blood volume. Your blood pressure is too high, so then it's going to cause hyperurination. You're going to end up getting rid of lots and lots of fluids, or your body's going to try at least to get rid of those fluids, as long as your diet and other factors help support that. And that's what you're going to see there in that chart on page 994. Just to follow one of the, I'll show you, just to follow one of those little flow charts, we'll start with the step number 1, and we'll just go through to number 6 so that you can understand what it is. And again, you can draw this out or use note cards to diagram it out, but you start off with some type of high blood volume. So you have high blood volume, that's going to elevate your blood pressure. So then what happens? There are some things that take place, some responses that your body's going to go through. First of all, your blood vessels are going to detect that increased blood volume and increased blood pressure. That's going to cause peripheral vasodilation. Everything's going to get a little bigger to allow for that increased volume. Your heart cells are going to detect that stretch, right? And ANH, or ANP, as it's sometimes called, is going to be secreted when that blood volume is increased. Your kidneys are going to sense this. That JG apparatus is going to inhibit renin, right? Renin is that hormone that secretes or that encourages erythropoiesis. So that renin production is going to be suppressed. And in your pituitary, you're going to have ADH secretion being inhibited. So in other words, your body's going to try to get rid of that extra water, and that's what you see in the reaction side. Increased renal blood flow is going to increase the rate of filtrate formation, and therefore more water being excreted in the urine. Decreased aldosterone, increased ANH, that's all going to cause a decreased sodium reabsorption, which is therefore going to allow your body to get rid of excess water, decrease the blood volume. And decreased ADH is going to decrease water reabsorption, and therefore less water returning to the blood, reducing blood volume, reducing blood pressure. So the major mechanism there is just by regulating the aldosterone and the ADH secretion and the effects of the kidneys, what we just went over in chapter 26. And if you remember, most of that action is happening in the distal convoluted tubules and the collecting system. So it's that last little phase of the nephron that's really being heavily impacted by those hormones, and the JG complex or JG apparatus plays a big role there. The next little section, you have some pictures on page 995 showing you some feedback loops with angiotensin and ANH in terms of high blood pressure and low blood pressure and the kidneys. The hormones are super important to understand. If you don't understand the hormones already, what does what, from chapter 18 or chapter 26, you definitely need to know them here in chapter 27. So pound them into your head if you must. The next section of this chapter goes into the regulation of the intracellular fluid. And the way I think of this is like this. So your body's made of like trillions of cells, right? So, but your blood is just one thing, right? Your blood plasma is just one thing. So it's super important that the composition of your blood plasma maintain homeostasis and be what it needs to be, because that blood plasma is going from your lungs up, filtering out through your CSF, right, all over liver, right, all over your body. So it's okay if 1 or 2 cells, or even a couple hundred cells, right, out of trillions, have a composition that's not suited for itself. In other words, if 1 or 2 or a couple hundred cells absorb a little bit too much sodium or absorb a little bit too much magnesium, right, kind of sacrificing themselves for the greater good. In other words, sometimes cells will keep more nutrients or sacrifice themselves for the good of the entire organism. And that is one way that intracellular fluid composition is regulated. In some cases, the body's just like, look, we don't care what you need. the blood needs to maintain this particular pH, so you need to take these extra hydrogen ions and shut the heck up, so to speak. So, you know, it's really important that your extracellular fluid composition, all that intracellular fluid, all of your blood plasma, you know, all of those extracellular fluids throughout the body maintain their proper composition. So sometimes little cells will have to take the brunt of that. So how are sodium ions regulated? This is all going to be kind of discussed in this next little section, all the individual ions and how they're regulated. If I say sodium to you and how it's regulated, you should automatically think, well, what hormones play a role? Aldosterone, right? Aldosterone is the key player in sodium regulation in the body, right? ADH is one of the major mechanisms for water reabsorption in the kidneys. Aldosterone is the sodium. And then you have some new terms, hyponatremia and hypernatremia, having too much sodium or not enough sodium. Then you flip the page on page 998, and there is a lot of terms there, and these are all of the different mechanisms for regulating blood sodium levels. So again, ADH is kind of a secondary. The major one is aldosterone. ADH plays a role because ADH and aldosterone pretty much go hand in hand. You also have ANH or ANP that are doing the opposite of what aldosterone and ADH are doing. So it's pretty important to understand the roles of those mechanisms and what they're doing in terms of a physiological response when your body needs sodium or has too much sodium. That little chart, table 27.6 on page 999, goes through the causes and symptoms of hyper and hyponatremia. You should be familiar with those causes and symptoms. They're pretty much, they're almost all the same throughout all of the ions that we're going to talk about. So, you know, just understanding some of the general symptoms is quite alright. We're going to stop this video here, and then in part 2 we'll continue with the rest of the ions.